Welcome back. Let's continue with the exposure step in the lithography process. Again, the outline here, we will be going through hardware and process parameters, and then we'll have a look at what kind of resolutions we can expect to achieve, and also look into the alignment process. Okay. Going through the process in steps here, we start with a mask. I actually have one here, so you can have a look at it in case you didn't see one before. So this is a mask. So we start with the mask and the substrate brought together to make them parallel. Then we can take them apart a little bit in order to enable us to move around the substrate so that we can align any pattern that we might have already in our sample to the pattern that we are going to apply in the photoresist. And this is what we do in a mask aligner like the one in the picture here. And then we can expose the resist to UV radiation through the shadow mask. And we are left with a resist film where part of it has been changed by the UV light. So that's the end result of our exposure step, is that we have the pattern transferred into the resist and ready for the development step. So again, going back to the composition of the photoresist, we have the three components, but by the time that we're done with the spin coating, we are basically reduced to two, because the solvent has done its part. It's enabled us to spin coat, and we have now baked it out. So we're left with only the resin and the photoactive component. And this film now has some optical properties. So it will absorb light at some wavelengths due to the photoactive component. And also typically what happens is that the absorption of light will actually decrease as we expose the resist to UV light. So this is sort of the analogy is that you can imagine that the photoactive component is basically used during the exposure. So it stops reacting to the light and it stops absorbing the light. So you can see an example in the graph out here of what the absorption of a resist film looks like when we start the exposure and when the exposure is finished. So you can see that we get this change here, that we go from something which is sensitive to light here around 350, 400 nanometers, and then we go down to something which is not sensitive at all in this wavelength range. Okay, so the hardware, we start with an exposure source. So we need something to generate the light that we want. And we typically use a mercury arc lamp. So this will emit the atomic spectral lines of mercury on top of the thermal light that we get from the arc itself. So this is a high, we put a lot of power into it, and we typically get only a little out, because most of it is lost due to heat and to all the radiation wavelengths that we don't want to use. The lines that we want to use are typically the ones at 365, 405 or 436. So those are the ones that you see in this graph here. The graph represents actually the light. Oh, I'm losing my pointer here. I think I lost the battery on that one. So this represents the light that we get at the mask and the substrate, is what we see in the graph there. So as we go through the optics here, so what you're seeing there in the drawing is actually kind of like a cross section of a mask aligner. We see the cross section here of the mask aligner, and the first thing that the light hits after it's been generated by the arc and reflected in a parabolic mirror, it hits the cold mirror, which actually dumps the white part of the spectrum and reflects the UV part into our exposure optics. And then it hits, the next thing the UV light hits is the shutter. So this is where we can close and open the light path in order to control the amount of light that we get to our sample. And then there is some optics there to help make the light uniform across a big area. And there's also the filter, which helps us select the wavelengths that we want. So the spectrum that we see in the graph there may be actually filtered down even more to contain, for instance, only the eye line, so that we get the lowest possible wavelength. And then we go on to the front lens, which collimates the light, makes sure that we get parallel beams hitting the mask and going down to the substrate. So that's the hardware of the exposure process. So we go on again with continue with the procedure. So we have, as part of it, we have the shadow mask that you just saw. So this is a glass plate with a chrome pattern. So we have our design already made in this plate. So this is something that we have commercially produced. So we basically send our design files to a company, and they produce a mask for us. And typically it has an anti-reflection coating on the chrome part of it, which makes that side brown. And this is something that becomes important later on to identify which side of the glass the pattern actually is on. Because the next step is now to load this mask into the mask aligner. So we load it in, and it's held in place in the machine, so that we can now start the procedure by loading our substrate into the machine. This is not necessarily completely parallel to the mask, so there is possibly an angle error there, which is called a wedge error. So the first thing the machine has to do is to perform the wedge error compensation. So we want to get rid of this and make the mask and the substrate completely parallel. So it's basically typically done by pushing the substrate against the mask. So it sits on a chuck, which is free to move, and then it comes into contact and becomes parallel with the mask. And at this point, we fix the chuck so that it no longer can tilt, and then we can move up and down completely parallel to the mask. Because the next step is then to separate so that we can move the substrate around in order to align to the pattern. So we align the two patterns, one on the substrate to the one in the mask. And then finally, we can go back into contact and open the shutter for a predefined time in order to give the desired exposure dose. Okay, so I can show you this in a video. So there you can see the mask going into the mask holder. And which is then flipped around and put into the machine. So this is where it's important to know what side is up on the mask. And then we load the substrate. You can see this one actually already has a pattern on it, which means that when we started the process, we can go in, look through the microscopes, and align the two patterns to each other. And then we can finally do the actual exposure. So we get the front lens out and the light starts. And that's basically the end of the exposure process. So there is a lot of different process parameters that go into this exposure step here. One of them is called the exposure mode. It can also be called the exposure type. So generally we have two ways of doing it. We have proximity exposure and we have contact exposure. The difference between them is the position of the substrate relative to the mask. So in proximity there is a gap between the two, and in contact they are pressed together. So there is of course some ups and downs to these two. So the good thing about proximity is that there is little or no contact between the substrate and the mask, which means that particles from the substrate or bits of resist from the substrate are not transferred to the mask, so it doesn't get dirty. And that means you can actually use this mask over and over again without cleaning and get the same result. The downside to this gap between them is that this reduces the resolution of the process. So that means that we get some effects in our pattern, especially when they're small. And with the contact exposure, it's basically the other way around. The upside is that we get the highest possible resolution, the best pattern transfer. But the downside is that we have very intimate contact between the mask and the substrate, which means that the mask will get dirty. And that means we can only do a few prints before we have to stop and clean the mask, and then we can continue. So there are some subtypes of the hard contact. So there is something that we call soft contact, and there is the hard contact and the vacuum contact. And I will go into detail with those now. The soft contact is sort of like the smallest force between the mask and the substrate. So this is where we use the same force as which was used during the wedge error compensation. So basically during the wedge error compensation, the machine will sort of establish a zero where the two are in contact. Then we move away for the alignment. And when we want to do soft contact exposure, we basically return to zero, which should be in light contact with the mask. So this means that we can do several prints, maybe a lot of prints, before we get a lot of dirt transferred to the mask. The other type is the hard contact, where we, before the exposure starts, we move back into contact and then apply an extra pressure in the form of a nitrogen pressure below, so on the backside of the substrate. So we're basically replacing the vacuum that normally holds the wafer to the chuck by a nitrogen pressure, and this forces the resist on the surface of the substrate into intimate contact with the mask. So here we can do something like 10 prints before we need to, before we start seeing the effect of a dirty mask. And sometimes another parameter in this process is the hard contact wait time, which is how long time we have between from the point where the pressure is applied and to the point where the light is actually exposed. And this is because sometimes when you apply the pressure, things have to sort of even out and fall into place. So you can see a difference between doing it immediately or waiting for a short period. You can basically force them into to a little bit more intimate contact by waiting a little bit. So the substrate bends a little bit and the resist maybe flows a little bit, and then you get a good contact. So the highest possible contact, or the best possible contact that we can do, is the last one, which is called vacuum contact, where we basically create a chamber around the substrate and evacuate this in order to force. So we basically pump the air gap between the mask and the substrate away and force them into close contact like that. So this is the best that we can do. I'll try to point you here. And you can see this rubber ring here around the chuck is basically, well, oh, sorry. If it's a possibility in the machine, then this can be inflated in order to create this vacuum chamber, and then we can pump out this chamber and generate a very, very good contact. But it also means that there is a high risk of the resist now sticking better to the mask than to the substrate, which means that when we separate afterwards, there is bits of resist left on the mask, which means that the next print will not be in good contact because there is this resist from last time left on the mask. So that means you have one perfect print, and then you basically have to clean the mask before the next one. Okay. Another parameter in the process is, of course, the exposure dose. So the exposure dose is calculated as the intensity of the exposure light times the exposure time that we set as a parameter in the mask aligner. So the unit is millijoule per square centimeter. It's a typical unit because we typically have intensities in the milliwatt per square centimeter range. So the optimal dose is, of course, a function of the resist, because, as I can show you here, different resists react differently to different wavelengths. So depending on the intensity, of course, but also the wavelength of your exposure light, you will get a different reaction by the resist. Of course, also the thickness of the resist and also how it was processed before we come to the actual exposure step. So there is the resist and the light, but also dependent on the developer. So dependent on whether you use one developer or another developer, and dependent on at what temperature you do the development, and could also be in some cases for how long you do the development, you will see a different optimal dose in that process. In some cases you will see that the exposure dose can also vary depending on which mask you're using, because the typical mask will be a standard soda lime glass, which actually absorbs a little bit of the UV light. Whereas if you have a very high precision mask, it will be in quartz, which has a very high transparency to the UV light. So you can typically see changes in the order of 10% between using one mask or the other mask. So it's something to keep in mind when you are adopting process parameters from other people, is that sometimes you can see a difference because of a difference in the mask material used. Okay. So let's talk now about what kind of resolution we can expect to get in this process. So what are the kind of sizes that we can resolve in the resist? So here is a theoretical estimation of the resolution limit. So as you can see, it's a function of the gap between the mask and the resist. The thickness of the resist layer is also a factor in the resolution. The wavelength of the exposure light is sort of how we would expect it to be, that the smaller the wavelength, or the shorter the wavelength, the better the resolution. I can give you an example here that if we adopt some kind of very optimal parameters, so that we have a perfect contact and a thin resist, the theoretical resolution limit is 0.8 micron. But if I accidentally mount my mask upside down, the light now has to travel from when it's shadowed by the chrome, it now has to travel through the entire thickness of the mask, which is around 2.3 millimeters. And that means that the theoretical resolution limit is now 43 micron instead. So as you can see that if we are working in the 5 to 10 micron range, putting the mask upside down in the aligner will completely destroy our pattern. Okay, so let's have a look now at what kind of things we can expect in terms of practical resolution, because one thing is the theoretical resolution limit, another thing is what can we actually achieve when we go in the clean room. So there is a lot of factors that affect the resolution. One of the things that is very important is what kind of contact do we actually achieve, both in terms of different positions on your wafer and also in terms of when you do different wafers on different days or at different times on the same day, do you actually achieve the same level of contact between the mask and the substrate. So what we typically see is that the constant K is typically higher than the theoretical 1.5, and so we can maybe expect something like a 2.5 constant there. It's important that we consider these kind of things when we do the design of our structures, because it's very important that the smallest structure or the smallest gap between structures that you do in your design should always be well above the theoretical resolution limit, because otherwise you should know that you're going to struggle to achieve a good result. So I would say 3 micron structures, that's possible every day, it should be possible every day. But if you want to go down below 1.5 micron, you have to expect that this only works when you're being really careful and probably also a bit lucky. So keep that in mind when you when you design your devices. So now I'm going to talk about two things where we talk about first print and alignment. So typically in a process there will be several mask steps. So in order to create a device. And the first layer we put on we call first print. And there's typically nothing on the substrate to align to. But then, so that means we have a blank substrate. And in some cases we want to align the mask to the flat of the substrate. So we would maybe have a mask that looks something like this. So the mask has a structure down there by the major flat in order to enable alignment to the flat, because that means we can orient the crystal of the silicon relative to our structures. And then there is some device in the center. So there is some device here in the center, and then there are these two structures out here, which are the alignment marks that we are going to use to align the structures for the device in the next step. Because the next step will then be, so this is what we are left with, right? We are left with some kind of process. And then in the next step, in the alignment step, we use the stage to align the substrate structures to the mask structures. So when we put the next mask on top, we get something that we have a new mask. So this has another set of device structures here, and then it has a different set of alignment marks out there. And when we look through the microscope in the aligner, we see something like this. So we have the substrate mark already there, and then we have the mask that we have on the second mask. So this is just sort of to define the terms that we are talking about, and you can find some help and some guidelines if you look at our internal wiki lab advisor for some help in the design process. So in the alignment, again, so we use the stage to move everything about. So we can start by translating into one of the marks so that they align. And this is what this is supposed to represent is that we have here we have one side of the substrate in the microscope, and over here we have the other side. So this represents the alignment of the structures that we would achieve in the center of our substrate. So you can see first we can move in so that they are roughly aligned, but we also need to rotate the stage a little bit to compensate for the angle there, and then finally we can translate in and do the final alignment. Okay, the accuracy. I mean, so this is always difficult, and this is also something that you need to take into account in your design. Is that you can probably do plus minus 1 micron, but in general there will be things that can push this can push the alignment further apart. So I think it's a good idea to expect up to 3 micron of misalignment. And remember to include this tolerance in your design, so that if you have 2 layers that need to be in contact, they should not be put like this against each other. They should overlap, so that you are always sure that you have contact between the 2 layers. Yeah, include some tolerances in your design to account for these inaccuracies, basically. So there are some different misalignments here. Normal translation and rotation misalignment, and the kind of accuracy that you can get depends on how the marks are designed. So obviously if they are so small that you can hardly see them in the microscope, then there's a problem. Also if they're so large that they that they don't fit in the field of view in the microscope, it's also a problem. And sometimes there are different tricks that you can use. You will get a more real-life feel for this when we actually go inside the clean room, because we will actually be doing alignment on one of the samples there. So you will try it yourselves. Of course, the more skilled you are as the operator of the equipment, the better the alignment you can get. Because sometimes it also means that you need to know your design, and you need to know the specific errors that you may have in your substrate or in your mask in order to get a perfect alignment. Sometimes you can get problems from previous processing of the substrate, and this is something which can cause the things that are down in the bottom. They are called run in and run out, because if you imagine that you do the first print, and then you do a thermal process before the next print. So then you could imagine, if you have a high temperature thermal process, that your substrate, including all the structures that you just processed on it, they expand. And when you cool down to room temperature, they contract, but they don't necessarily come back to exactly the same point. So you can get some gain in your image, which means that when you now try to align to the next mask, you cannot get both to be in the correct position at once. So if you just compare down here, right? So you can see if we put this one to be correct, this one would be much further out. And the important thing here is that when you do this, when you have this problem, align both sides. So this is supposed to be the one you look at in the microscope in the one side and in the other, and this is then the device itself, right? So remember always to do them symmetrically wrong, because in that way you actually get a good alignment of your device. Because in the center you can still get good alignment as long as the error is sort of symmetrically wrong out here, right? Another thing that can cause this problem is if you have a substrate and in the first layer you actually grow an oxide on top of it or deposit an oxide on top of it, then you can introduce bow in the substrate, and this also represents the same thing like a gain in the image, so you can get these problems again.